Welcome back, and let us continue the discussion on this premixed flame analysis, where we are doing the analysis of a simplified system, and based on the assumption we are taking a 1D premixed flame, and this is where we stopped. And just to quickly brief about, there are certain assumptions and which are there: one dimensional steady flow, there is no pressure change across this flame front, then Lewis number 1, Cp all are equal, single step chemistry. So, these are the, and this is my control volume. Now, so first thing that we will start our mass conservation, which is an important thing. So, it will be dx of rho Vx equals to 0, or one can write equals to rho Vx, which is constant. Now, that is my mass conservation. Now, we will look at the species conservation. So, this for individual species, this is my species conservation, because individual species they will react. And now, when I apply now Fick's law of diffusion. So, if we apply Fick's law of diffusion, what we get with the application of Fick's law of diffusion, we get d of m dot yi minus rho d by dx by dx equals to m dot I. Now, what we have assumed, it is an single step reaction. So, that is our simplified analysis, single step global reaction. So, you can think about 1 kg of fuel, nu kg of oxidizer, that will give you nu plus 1 kg of product. Okay. So, I can write m dot f 1 by nu m dot oxidizer equals to 1 by nu plus 1 product. This is okay. So, you get this fuel oxidizer mass flux and the products mass flux equated. Now, we can write also in terms of individual species, because now individual species mass transfer equation if we write. So, how it looks like for fuel, it would be d yf by dx minus rho d by dx equals to m dot f. And for oxidizer, if we write m dot d oxidizer by dx minus rho d by dx nu m dot f, triple dot f. So, one can notice here in the diffusion law we have d, which is constant, because that is one thing that we have assumed they are going to be equal. Now, similarly, we can write for the products. So, this would be m dot d product by dx minus d dx of rho d, which is minus mu plus 1. So, everything is written in terms of m dot f. That means, if we know one of the mass flow rate, whether it is a fuel or oxidizer something, we can find out the rest. So, we got species mass conservation equations in terms of individual species like fuel, oxidizer and product. Now, we will write the energy conservation equation, which is m dot Cp dt by dx minus ddx rho dCp dt by dx raised to minus summation of Hf0. So, that is the contribution for the species consumption or due to the reaction. So, that is my. Now, this right hand side of this equation, the right hand side of this equation, one can write in a slightly different format, like I can simplify that thing like H naught F I m dot I equals to minus H naught fuel m fuel plus H naught F oxidizer nu m dot F minus product nu plus 1 m dot F, which will in turn become H naught F I equals to minus m dot F delta H C. So, that is a simplified way one can basically represent that right hand side, where delta H C is nothing but your heat of combustion, and this one can write Hf fuel plus nu Hf oxidizer minus nu plus 1 product. So, this is how one can represent that. Now, we have another assumption, which is Lewis number 1. So, that tells you kappa is rho d Cp. So, using that we can rewrite this 6 point. So, we will rewrite 6.7a, and what one can write now, m dot dt by dx minus 1 by Cp ddx of kappa dt by dx minus m dot triple dot F delta Sc 1 by Cp. So, using the other thing, now whole idea here is to, or the rather the objective is to find an expression for laminar flame speed, expression for laminar flame speed. That is what we want to do. Now, one can correlate that or relate to that the mass flux m dot, like m dot equals to rho u SL. This is a very interesting expression where rho u stands for density of unburned mixture, and SL is your laminar flame speed. So, approach is to assume a temperature profile that must satisfy the boundary condition, and then we can integrate this equation. So, we can assume a temperature profile and which will obviously satisfy the boundary condition, then this temperature equation if we integrate, then we can get that. Now, what are the boundary conditions? If we look at those boundary conditions first. At the upstream, you have T which x tends to negative infinity is T unbound, and gradient would be when x tends to negative infinity, gradient is 0. Now, that is an upstream. Now, downstream at the product side, you have T x tends to plus infinity equals to T bond and dt by dx, while x tends to positive integration infinity. So, 6.9 C to D. So, this is the situation. This is your upstream and this is your, this is for example temperature profile, this is downstream. So, you get these two conditions. So, if you put them, this is my x negative infinity, this is x positive infinity, and this is the direction of the x, and we assume an temperature profile. So, the one which is presented here is a linear profile. So, this is the upstream boundary condition, this is the downstream boundary condition, and this is the delta. See, this delta is the flame thickness where you have this temperature. Now, the assumption here is that this Tx is linear. So, this is what we assume the temperature profile, and the temperature goes from T unbound to T bound, and the distance between which this temperature is, so that is the delta or the flame thickness. So, within this distance temperature goes T unbound to T bound. Okay. Now, we integrate 6.7 b and we get m dot T unbound and T bound minus kappa by Cp dt by dx, which is limit 0, heat of combustion by Cp minus infinity dx. So, if we write m dot Tb minus Tu, this one can write minus delta is C by Cp minus so. Now, the limits of the reaction rate integral, this is the one can be switched to the temperature from space coordinate. The reason is that m triple dot this m dot f is, this guy is non-zero between Tu and Tb. So, over delta. So, the dt by dx was T bond minus Tu by delta, or dx is delta by Tb minus Tu dt. Now, we switch these things. Now, this one if we use here in 6.11, then what we get? Now, using this in 6.11, we get Tb minus Tu equals to minus delta is C delta by Tb minus Tu. Now Tu Tb dt. So, we switch the limit of the integration from the spatial coordinate to the temperature coordinate. Now, the average reaction rate which one can define, this is the average reaction rate which is now Tb minus Tu. So, we term that thing is a average reaction rate. So, if you use this information of the average reaction rate, we can finally simplify that term to be minus delta is C delta. So, that is the expression one get. Now, here in this particular equation, if you look at it, there are two unknowns. Number one is m double dot, m dot double prime, and second is delta. So, these are the two unknowns. So, we have right now one equation and two unknowns. So, that means to get the complete solution, we need one more equation. Now, what we can assume? We can assume the reaction rate is much smaller within the first half, within the first half of delta. That means, which essentially says between x equals to minus infinity and x equals to delta by 2. So, we can reevaluate equation 6.10, and from x equals to minus infinity to x equals to delta by 2, if we do that, we get T equals to Tb plus Tu by 2 and dt by dx. Here x is delta by 2, Tb minus Tu by delta. So, now one can write 6.10, we can rewrite that, or that becomes rather delta by 2 minus kappa by Cp equals to 0. So, here is my second equation. So, we have two equations now. Equations are 6.15 and 6.17, and we have to solve for delta and m double prime dot. So, once we solve these two equations, the solution gives you m dot equals to 2 kappa by Cp square minus delta is C, Tb minus T unbound half. So, that is one solution that you get for this, and the delta becomes 2 kappa by Cp m dot. So, you get the solution for these things. Now, we apply the definition of laminar flame speed. So, we applying the definition of SL, which is m dot by rho u, where alpha is kappa by rho u Cp and heat of combustion is nu plus 1 Cp Tb minus Tu. So, if you use all these expression, rather combine them together and you use the solution of delta and m dot, what we get? SL equals to minus 2 alpha nu plus 1 average reaction rate by rho u to the power half, and delta equals to 2 rho u alpha divided by nu plus 1 half. This is my 20, and one can see, if you use the information of SL here in the delta, one can write this delta as 2 alpha by SL. So, that is what one can write. So, that is a nice correlation you will get between SL, that is the laminar flame speed, thermal conductivity and the flame thickness. Now, we can look at, so that is one thing, there is a this thing is that there would be some factors which are influencing this. So, we look at those factors that influence SL and delta. Now, one thing immediately you can notice that SL has a, from these two equations 6.20 and 6.21, you can immediately notice that SL has a dependency on temperature. SL or delta is a function of temperature. Now, we first consider some temperature, approximate temperature scaling, some approximate temperature scaling, which will get you that alpha is proportional to T unburned to the power 0.75 pressure to the power 1, and reaction rate would be proportional to T unburned to the power n p to the power n minus 1 exponential minus A by RU TB. So, here n is the overall reaction order and T bar is the 0.5 of TB plus TU. So, that is what one can get. Now, if you combine these scalings, which will allow you to get an expression for SL, and that will look like now, it will be T bar T unburned to p to the power n minus 2, whereas delta is proportional to 0.375 exponential A by p to the power n by 2. So, what one can notice here, there is a strong dependence on T on both Tu and Tb, and flame thickness, the delta is inversely proportional to SL. Now, if you take some number for n, for example, let us say n2, then SL becomes independent of P. That is a specific case, one can look at it, that the dependency of SL on P and all this. Now, there are different correlations which actually exist, some for let us say for stoichiometric methane air case, methane air mixture, the correlation is that SL is 10 plus square, and this is based on temperature. Based on pressure, same SL, this is 43.5. So, simplified analysis can capture the effect of temperature, but not the effect of pressure. So, you can see these are again based on some simplified analysis. There is a correlation. See, SU is nothing but your SL that we are discussing. So, laminar burning velocity, the pressure in the atmosphere when it changes, the data is in the lower atmospheric condition, data is quite scattered, and then the burning velocity at the higher atmospheric condition follows some correlation, but at the lower pressure there is a quite a bit of scatteredness which is observed. At the same time, if you see this is on the equivalence ratio, this is phi curve or the axis, this is percentage of methane, and this is normalized, and this is again burning velocity. What you can see clearly, and this is a pretty much an very unique characteristics of hydrocarbon fuel, that you can see if you plot the laminar flame speed corresponding to phi, you get some peak around this point 1, that means around phi equals to 1, that is the stoichiometric. So, there will be peak. Before that, this is phi less than 1, that means the lean condition. So, the lean condition temperature dependency, I mean temperature would be less and it is completely burned. So, it is increasing, because as the phi is increasing, fuel is increasing, temperature due to reaction is increasing, SL is increasing. It reaches a maximum limit around phi equals to 1, which may not be exactly 1. Then after that, this side is the phi greater than 1, where again it starts decreasing. This is one of the unique characteristics that you find in the hydrocarbon fuel. So, but other fuel also you can estimate this, and again this is an analytical, there are analytical expressions which are available. So, you can actually take it up as an small work assignment and calculate this. So, we will stop here and continue the discussion in the next lecture.